All right, welcome to Geology, everybody. Continuing our chat about geologic time. Let's think about what we've done so far. Well, first, we just set the table and said that yes, the Earth's the amount of time that the planet's been here is vast, 4.5 billion years old. Then we said we got to break that down into two techniques that have enabled us to figure out how old the planet is and what's been going on and unravel the history of the planet. Starting with relative dating, should have already done that. Those are the techniques that say, okay, this rock's older than this rock because of cross-cutting, superposition, all of those ideas. That's just older, younger. That doesn't put numbers on it. Today is let's put some numbers on it. How have we figured out how old some of these rocks are? We do it by using radioactive decay. Now, I feel like carbon dating is a thing you hear in TV shows, movies here and there. And this is what they're talking about. Carbon dating itself isn't necessarily ideal for all of geology. We need different tools, but it's the basis of it is how it works. So radioactive isotopes like carbon-14 predictably decay down to a more stable isotope. In this case, carbon-14 turns into nitrogen-14. Or if you want to come down here, potassium turns into those two. Uranium turns into that. Rubidium turns into that, right? So it's specific to each one, right? So it's a random process. This is the thing that is tricky about it. Any individual carbon-14 atom, if I could hold one in my hands and sit there and watch and wait for it to decay, it does so randomly. However, the amount of times that it happens over a given period is predictable. It doesn't change. So when I do a lab with this with high school kids where we get out a whole bunch of dice, like hundreds of die, and we roll them all. And I mean, what's more random than a die roll? You know what I mean? We roll them all, and if it's a one, we say it decayed, and we put it over there to the side and we count it. And if it didn't, then it's still radioactive, right? Essentially in our little model. Then we roll again and get rid of them. And we roll again and get rid of them, and do that over and over and over again. Again, any one individual event is a random occurrence. Any individual atom of carbon-14 that disintegrates to nitrogen-14 is a random occurrence. But it happens at very predictable rates. That dye lab, I've done this for a couple of years now, the numbers are coming back like the same every single time. Sorry, losing you. The smart board's turning back on. Sorry about that little glitch there. So the amount of times that it happens is predictable. Therefore, we can use it as as a measuring stick. We can say, hey, if I take a rock that commonly has potassium in it, and some of that potassium is radioactive, and I know that through time, some of that will break down and turn into those. And we have figured out that the half-life for that is that 1.3 times 10 to the ninth. That's 13 with 8 zeros after it. It's a long time. But if you can use sensitive equipment and measure how much of this is there relative to how much of this, and we know that it takes that long to get rid of half of them, you really have got a pretty good measure on how old the rock is. The amount of time it takes it for half of a sample to decay is known as the half-life. Okay? Don't forget your book here, page 12, if you have the PDF version. This is going to talk about how some of this works. There's more to read here than I'm going to go through. The trick to it is that, so after one half-life, you lose half. So after another half-life, what do you lose? Well, you lose half of that. You don't lose the rest. You know what I'm saying? So here it is after 0 half-lives, you've got 100% represented by this bluish orangish color. After one half-life, you're down to 50%. Then after another half-life, you lose half again, so you're at 25. And after another half-life, you lose half again, so you're at 12.5. 6 and a quarter, right? 3.125. They keep on going in half and half and half and half and half as it goes. So again, the trick then is just to grab a rock, grab a piece of a granite here that has feldspar in some of the minerals, which we'll learn about eventually, and the potassium in there. See how much there is relative to the other isotopes, and boom, you can calculate the age. I'm not saying it's that easy. You can't like hold your thumb up to it and do it. It requires some equipment, but it works. It's possible. Okay, these are the common ones. Going back to my little note sheet here, this is the one from the New York State reference tables. Carbon 14 is a relatively short half life, so it's good for things that are relatively young. First off, it has to contain carbon, so it's usually organic things, but good for things that are relatively young. This is 5,700 years. If you end up going in half, in half, in half, in half over and over and over again, eventually it gets so low that it's really tough to determine what is that versus half of that versus half of that. The line gets so approaches zero and gets so flat that it's not really useful anymore. So you want it kind of in this range. So once you get much past, say, 5-ish, 6-ish half lives, so 5 or 6 times that, carbon 14 is going to be all gone. But that's where these other ones are more valuable because they've got much longer half lives. So that can get us deeper into Earth's history. And that's what this version of pretty much the same graph um, shows us here. I like it. The useful range for these, which will be how long? All right, some cool stuff there. That's really going to be most of what we do with radioactive decay here. Though, I'd anticipate that you're going to see some questions on this. What I did here was I stole pieces of 2 questions that I use. These are like New York State Regents questions. The ones I make up might look similar. So if you had to figure this out, what you would do, and when I took these tests, I would like write these little charts in the margins to try to figure it out. After 0 half lives, you have 100% of the original material remaining, whether that be carbon 14 or whatever. And how many years does that take? So after 1 half life, there's 50. After 2 half lives, there's 12.5. After 3 half lives, and again, I would like do this in tests. I can't do this in my head. Then how long does that take? Well, since we're talking carbon 14, it takes 5,700 years. If you change that to potassium 40, it takes 1.3 times 10 to the ninth years. The classic mistake is that people say, well, I cut in half, I cut in half, I cut in half, I cut in half. Then they come over here and they want to just double it, double it, double it, double it. It's like a weird thing that happens in your head. That's not how it works. This is just add 5,700, add 5,700, add 5,700. And I'm going to bust out a calculator to make sure I don't screw it up. 0.28. Right? Another 5,700. 28.5. Okay. That's what that question had you do, was just answer one of these ones and fill it in that chart. So if I were to ask one about uranium 238 and it takes that long, this section is always going to look the same, right? That's the same for every single isotope. At 0 half lives, you have 100. At 1 half life, half of that. 2 half lives, half of that. 3 half lives, half of that, and so on. The number of years you would have to add up based on what you see in this. And you can use this chart. Don't say, oh, geez, I got to memorize that. No, hold on to that. When you do the quiz, you can have that there. You can have a textbook open. You can use that one as well. Graphically, what does that look like? 0 half lives, we have 100%. After 1 half life, we have 50%. After 2 half lives, we have 25%. After 3 half lives, 12.5, and so on. And that's again why once you get out to like 5, 6, 7 half lives, this line would be so close to 0 that it approaches useless. This is not years. This is number of half lives. But you can stick the years in there because we know how many years each one of those takes. Sound good? So check out this chapter a little more thoroughly as well. Basically, this graph and that one I just showed are the same. One uses bars, one uses points. It's all good. That's good stuff. And then really, so yeah, to wrap it up, and they talked about it up here. I didn't talk about this in videos, but I wouldn't ignore this section. This is where you can take both things now and use them together. So there's things called index fossils where we know we've studied enough, we've figured all of this out, we know when certain animals were alive. Excuse me. And if these animals create fossils, get buried in the right environment, and we find that fossil in a rock, that's a sign to me that, oh, this rock therefore must be this age, right? So I was in some Silurian rock yesterday in Rochester. If I went down there and I dug up a fossil and I found it, I knew it was Silurian already, right? But like if I found an index fossil that indicated that, I'd say, oh, this is therefore Silurian rock, because I know that this animal was alive during the Silurian. And then if I went higher in the section, rocks that are above that, therefore I know that that's younger. And if I went down below that, I know that it's older. So between using the relative dating techniques we did in the last video, throwing in this idea of index fossils, now that we've sorted out the history of life and organized it and figured it out, and hey, if I find a dinosaur, I know I'm not in Paleozoic rock anymore, I'm in Mesozoic rock, right? You're never going to find a dinosaur fossil in upstate New York because the rocks are much older than dinosaurs. But combine that with the index fossils and then throw in the idea that we finally figured out this radiometric dating idea to throw numbers on there, and through millions of people working millions of hours and doing all of this in different fields and combining all of these ideas, we've been able to put together a pretty solid history of the planet. All right. One part I'll tell you to skip for now. If you're reading these chapters thoroughly, it's great. I appreciate it. This magnetic chronology section, I'm going to save that for tectonics because this has to do with what goes on at a certain type of tectonic boundary. And I think it fits better there than here. So you can skip magnetic chronology in this chapter if you'd like. But this 19.6 is an excellent little wrap up of what we've been talking about here this week. So check it out. A couple questions down here if you want to try. And that's it. That'll be it for this module. And then we'll move on to tectonics in the next one after the quiz. Thanks, folks. We'll talk to you soon.